Hello everyone. Today we're going to talk about how to work with vectors. As you recall, vectors are quantities that have both size and direction, and we represent them by drawing arrows. Now on the screen you'll see several vectors and a little compass to indicate direction. So a vector can represent any quantity that has size and direction. So let's define what these vectors are. So let's say that vector A represents a displacement. "20 meters east." All right, and the little compass indicates east. Now, I also have vector B here. Now, vector B is also a vector pointing east. However, I don't get to choose its value. We are working with vectors graphically. Once I draw an arrow representing 20 meters east, every arrow I draw from then on has to adhere to the same scale. So I have a ruler down here. So let's measure our arrows. And I see that vector A is about 4 centimeters long. And let's go measure vector B. So vector B is about 7 centimeters long. So that means that if vector A is 20 meters, the scale determines the size of vector B. So the size of B, now we indicate the size of a vector by using an absolute value brackets, right? So this would mean the magnitude of B. And if you remember, magnitude is just a fancy word meaning size. And the size of B would be equal to, well, that would be 7 centimeters divided by 4 centimeters times 20 meters. That equals 35 meters. So vector B is equal to 35 meters east. All right, well, vectors C and D are the same length as A. So vectors C and D over here all represent vectors that are 20 meters long. But vectors C and D are not the same as vector A. For two vectors to be considered equivalent, there are 3 things that need to be true. They need to be the same type of vector. They need to be the same size vector, that is, have the same magnitude. They also need to be pointing in the same direction. So we make a note that vector A does not equal vector C, and it does not equal vector D. For vectors to be equal, well, you need 1, same size. 2, same type. That is, you can't have a displacement vector to be the same as a velocity vector. And 3, same direction. So to be equivalent, vectors need to be the same type, They need to have the same length. They need to be in the same direction. All right, so now that we've defined how to draw the vectors and how to draw them to correct scale, the next thing we're going to do is look at how we can do math with vectors. Okay, so we have our vectors A and B, and these represent two displacements, which are quantities. And just like scalar quantities, vector quantities can be added, subtracted, and even multiplied, although we'll hold off on multiplication to a later section of the course. So how would I add these vectors graphically? Well, when we talk about graphical addition, we're talking about working with the vectors drawn to the correct size. We're going to see that this can be problematic. You have to pay attention to the scale, which means you have to be careful how you draw the vectors. Well, first, if I want to add these vectors, what I need to do is arrange them so they are arranged tip to tail. So that's the first thing we note. To add vectors, arrange the vectors being added tip to tail. Or, if you like, tail to tip. All right, so what does that mean? That means simply if I want to add these vectors, I need to select them. And I need to arrange them tip to tail. That is right there. This is what we mean, tip to tail. All right, then this would represent vectors A plus B. But remember, our scale here was that 4 centimeters equaled 20 meters. So we represent the answer of combining our two vectors. We draw the vector called the resultant. The resultant or vector R is the result of combining the vectors. Is the resulting vector from adding A and B. And remember, we're putting little vector hats on our vectors, so we know that we are talking about vector quantities here. All right. Well, if I want to know the answer, then I have to use a ruler to measure the scale. So if I measure vector R, I see it is 11 centimeters. So vector R, the size of vector R, or the magnitude of vector R, is going to be 11 centimeters times 20 meters over 4 centimeters. Because remember, that was my scale. And so that means that the size of R, well, let's see, that's 11 divided by 4. So that means that vector r is 55 meters, and vector r is 55 meters east. Now, you may be saying that that's obvious. Well, and it kind of is. But what happens if A and B are not in the same direction? Okay, so here are our vectors drawn again. But now we've changed the direction. So these are not the same vectors as before. So I will label vector A here, and I'll label my vector B. But let's make a note here that vector A is now equal to 20 meters west. And vector B is equal to 35 meters north. So I would like to know the result of adding vectors A and B now. Well, the vectors we add are arranged from tip to tail, but the resulting vector is always drawn from the start of the first vector to the head of the last vector. Here is my vector r. Now, this is not going to be equal to 55 meters anymore because the vectors are not going in the same direction. Furthermore, the direction here is the vector is at an angle. So to determine these two things, I need both to measure the length of the vector as well as the angle. So let's deal with the size of the resultant first. And I need to place the ruler along the resultant to find out its length. And I see here that the resultant is about, let's call it about 7.5 units long. So if I want to find the magnitude of r now, I need to use the scale again. The size of vector r is going to be 7.5 centimeters, that's how long it is on my page, times, well, remember, it was 20 meters where it was 4 centimeters. And so that means the size of the r is equal to it's about 37.5 meters. But what about the direction? Well, it's pointing northwest, but I can do better than that. I would like to measure the exact angle, so let me move the ruler out of the way and get another measuring device. I place the center on the protractor at the beginning of R, and I see that this is about, let's call it 60. It's about from here to there is about 65 degrees. So vector R is equal to 37.5 meters, 65 degrees northwest. So the principle is the same. The vectors you add are you arrange your vectors tip to tail. But the resulting vector is from the start of the first vector, or the tail of the first vector, to the tip of the last vector. And this technique works with any number of vectors. And it doesn't matter which order you add the vectors. Whether I add A to B or B to A, I will get a resultant of the same length and in the same direction. That is not true, however, if we subtract vectors. So let's take a look at how we subtract vectors.